Let's strip a computer down to its physical reality. You have the CPU, the RAM chips, and the storage drives. Just raw, bare metal circuitry waiting for instructions. If every application on your device tried to grab the CPU and memory at the exact same time, the hardware wouldn't know what to do. The immediate result is instant conflict, a total lockup, and system failure. To prevent this, your computer relies on a core piece of software sitting directly between the hardware and your applications, the operating system. To understand how it orchestrates this chaos, think of your computer as a massive, high-traffic airport. The physical hardware, the motherboard, the memory, and the storage drives are the physical infrastructure. They are the runways, the terminal gates, and the fuel systems. Your applications, like your web browser and games, are the airlines and the passengers. They are constantly competing for space and requesting services. This image of an air traffic control tower overlooking the runways illustrates our operating system. It acts as the centralized command structure, scheduling resources, resolving conflicts, and directing all the activity. Modern computing only functions because the OS enforces strict privilege separation, precisely schedules resources, and abstracts the hardware to manage an endless stream of demands. This orchestration requires a strict architectural divide. To prevent security breaches and systemic crashes, the operating system separates into distinct permission levels. Looking inside the tower is the kernel space. This highly privileged core has unrestricted access to hardware. Outside the window are planes, representing the user space, a restricted environment for standard applications. A hard barrier prevents apps from touching the hardware directly. Whenever an application needs to open a file or connect to Wi-Fi, it must use a mechanism called a system call. Just like a pilot radioing a request to the control tower, the app asks the kernel to perform the action on its behalf. The kernel checks the request and executes it safely. Because the kernel maintains absolute authority over the hardware, a single buggy application crashing in the user space won't take down the entire computer. Beyond security, the OS manages finite resources. It decides how much CPU time each program receives, rapidly switching between them for seamless multitasking. It also allocates specific, isolated blocks of RAM to active processes, ensuring data never overlaps. If physical RAM runs out because you have too many applications open, the OS utilizes virtual memory, temporarily moving less critical data to your storage drive to keep the system stable. This management extends beyond the CPU and memory to external hardware, utilizing device drivers. Drivers form a hardware abstraction layer. They act as universal translators, taking a generic print command from your application and converting it into the specific electrical signals your exact printer model requires. The OS applies this same abstraction to storage through file system management. It organizes raw data into clear, hierarchical directories with specific paths, metadata, and user permissions. By handling all these granular hardware realities behind the scenes, the OS provides software developers with a predictable, stable environment. They can build complex applications without needing to understand the underlying circuitry of every device. All of this complexity is hidden behind the OS interface, the only part of the system the end user ever actually sees. This brings us to the graphical user interface, or GUI, shown here in Windows. It relies on visual representations like the taskbar, shortcuts, and menus. Using a GUI is like a modern navigation app. You just tap a destination, bypassing the underlying routing logic. The alternative is the command line interface, or CLI. As seen in this Ubuntu terminal, users input specific text-based instructions to manipulate information. Relying on the CLI is like typing exact GPS coordinates. It requires strict syntax, but gives you unparalleled speed and granular control. Whether you click a glossy icon or type a rigid command, the end result is the same. Both actions simply submit system calls to the underlying kernel to manipulate the bare metal hardware. Because the physical constraints of hardware vary wildly from device to device, no single operating system can be universal. A server operating system, like Linux or Unix, sacrifices rich graphical interfaces. Instead, it prioritizes a headless design built for multi-user scaling and maximum uptime. A mobile OS, like iOS or Android, operates under entirely different constraints. It has to prioritize extreme power efficiency and rigid application sandboxing to extend battery life. Embedded and real-time operating systems are even more specialized. They govern hardware with strict, guaranteed response times, running everything from IoT appliances to aircraft controls. Despite these different forms, every operating system shares one core feature. It serves as the foundational baseline of cybersecurity. Long before you install a third-party firewall or antivirus, the intrinsic architecture of the OS is already defending the hardware through authentication protocols, user permissions, and strict kernel isolation. Every time you log in, swipe a screen, or save a file, you are relying on this invisible manager to enforce the rules, arbitrate the resources, and keep the modern digital world functioning predictably.